Okay, so this is the first video lecture of Earth and Space Science 9, looking at topic 11, lesson 1, movement in space. But we're really going to be looking at objects in the sky in this lesson. But this whole topic is about the Earth, the Sun, and the Moon system and how they all kind of interact with each other. So go ahead and open your books to page 488 and take a look at this picture of the Sun. And basically, what do you think is happening to the Sun here? I would hope that you'd think, oh, wow, it looks like we're missing like the bottom half of the Sun here. And what you're actually looking at is a partial solar eclipse, okay? So down here, it says, as the Moon travels around Earth and Earth travels around the Sun, the three objects interact with each other. What are some of the patterns you can observe in the interactions among Earth, the Sun, and the Moon? So there are many more phenomena that involve these three objects. So not just solar eclipses, but lunar eclipses. We're going to talk about tides in this topic, and just a few other things that these three objects, they have effect on us. Okay, now every topic has a phenomena that we're going to kick off with. So phenomena is like an event or something that's happening, and it makes you question what's going on here. And so the phenomena that we are going to look at is tides, and how tides are actually related to where the Earth is in space. So I'm going to go ahead and read this paragraph, and then I'm going to open up a video, and we're going to watch it. Okay. So it says, the ebb and flow of the ocean's tides are as steady and sure as the passage of time. Engineers are investigating how to put the power of the tides to work as an alternative to the burning of fossil fuels. In this quest activity, you will produce a model to help visitors to a tidal power company understand why tidal power is a reliable source of renewable energy. You will explore how and why our position within the solar system causes tides and their patterns. The model that you produce will demonstrate how tides happen. So at the end of the topic, I will actually give you kind of like this poster paper. And you're basically going to put down things that you've learned throughout this topic to explain, the phenomena that you're seeing. And this is actually part of the new science standards that Minnesota has adopted the last couple of years, and we need to be fully implemented in the coming years. So this is new for me, this is new for you, and so we're just going to go through it together. Okay, so I'm going to exit out of this because now, I should say that like after every little mini lesson, these are like little check marks, and so I'll have these printed off at a later date. But like you'll ask yourself, okay, can I see the connection and the patterns I see with tides, and how they affect Earth? Do I realize that as the Earth rotates, there's a pattern for when we see those tides? And so those are kind of like mini, do I understand what's really going on with this topic? Okay. And then at the very end with your little poster paper, there's a rubric. And so again, I will have these displayed so like, okay, yeah, I can do that. I understand what's going on here. Okay, so I'm going to kick off the video, which is here. Oh, I got to back up. My bad. And we'll just go full screen, see if this works. Okay, so there's this interactivity, and you would do this on your iPad, but I'm just going to do it in the video. It's as sure as the tides. How are tides related to our place in space? You use electricity every day in many different ways, from playing video games to lighting your room. Today, power companies generate most electricity by burning fossil fuels, which are non-renewable resources. Non-renewable means that, you can't get it back. Okay, so like coal, formed millions of years ago. They are the remains of ancient plant and animal matter. And so we call them non-renewable because it takes a really long time to form them. Okay, but people hope to generate more and more electricity with renewable resources such as the sun, wind, flowing water, and tides. Tides are a more predictable source of energy than sun or wind. Why are tides such a predictable source of energy? Where does the pattern of the tides come from? Discover the answer in this quest. So basically what they're showing you here is that we have these turbines and they're underwater. Okay. Now, when the water level is above the turbine, they're not moving. These turbines only move when the water level is about to change. Okay. During the tides, between a high tide and a low tide. All right, let's move on here. So here's the short video.
October 29th, 2012. Hurricane Sandy made landfall on the northeastern coast of the United States. Water rushed into subway tunnels in New York City. Waves 32 feet high slammed the Jersey Shore. Streets flooded and homes were destroyed.
This is probably about 30 yards from the actual railing here at the seawall, but it's as high as the park benches there. This is a record surge for Battery Park in New York City.
Most of the destruction from Hurricane Sandy does not come from wind or rain. It comes from the ocean's great power in huge tidal surges, or storm surges, that wash onto the shore. These surges are the result of drastic changes in sea level that can occur during major storms. It's estimated that the energy from these tidal surges caused more than $68 billion in damage. A tidal surge during a hurricane obviously has a huge amount of energy. But there's also a great deal of energy in daily tides. Do you think it's possible to harness that energy to supply our daily needs? It's a question some enterprising companies are trying to answer.
Almost 3/4 of the earth is covered in water, and almost 3/4 of the electricity in the world is used within 200 miles of an ocean. If somehow you could put the two of these together, it would be a breakthrough in terms of how we generate and distribute electricity around the world.
Tides are the normal rise and fall of sea level. Twice a day, the sea level rises over several hours, reaching high tide, then begins to fall over several more hours, reaching low tide. Take a look at the difference between high and low tide here. With time-lapse video, we see the water level rises at high tide because a very large volume of water moves towards the shore. And the water level drops at low tide because that large volume of water moves away from the shore. This movement of large volumes of water back and forth contains a great deal of kinetic energy, or energy in motion. Scientists call this hydrokinetic energy, hydro meaning water. So, would it really be possible to harness the hydrokinetic energy of tides to generate electricity? The science concept behind hydrokinetic energy is not that far off from what humans have been using for thousands of years. As long as 2,000 years ago, the Greeks used hydrokinetic energy of moving water to turn large grindstones to grind wheat into flour. In the late 19th century, water turbines were first used to convert hydrokinetic energy into electricity, or hydroelectric energy. The Ocean Renewable Power Company has placed large hydrokinetic turbines in Cobscook Bay, which is part of the Bay of Fundy in Maine. The Bay of Fundy is ideal because it has a huge tidal range. The difference in water level between high and low tide is 17 meters, or about 55 feet. The hydrokinetic energy from the moving water in and out of the bay is what turns the turbines and produces hydroelectricity.
The basic technology that ORPC develops is a hydrokinetic turbine, machines that transfer that motion of the water into electrical energy from a subsea generator.
The underwater turbine acts just like a paddle wheel. The hydrokinetic energy of the moving water turns the blades, transferring the kinetic energy to a generator, and produces predictable and clean hydroelectricity. Thanks to its power and reliability, tidal energy may just be the next chapter in using water as an energy resource and be the wave of our energy future. Now it's your turn to research tidal energy as a potential source for electricity. Go online and see if you can find other places in the world that use the hydrokinetic energy of tides to generate electrical power.
Okay, so it says tides are the natural daily rise and fall of ocean water. High tide occurs when the water reaches its highest level. Low tide occurs when the water reaches its lowest level. The difference between high tide and low tide is the tidal range. Different places on Earth have different tidal ranges. So this is obviously time-lapsed video. So how did the tides change the appearance of the shoreline in the video that you just watched? Right? So I mean, before and after. You can say like, oh, the water level is, or the water is closer to the shore. The water level is higher near the shore. The boats, with buoyant force, more boats were lifted off that were docked at the shore. So lots of things that you could write there. Okay, your quest will focus on the site of a tidal energy project in Eastport, Maine, where a power company has installed underwater turbines near the mouth of the Bay of Fundy. Click through the images to learn why a company would choose the Bay of Fundy as a site to generate electricity from tidal power. So here's Eastport, Maine, a group of small islands near the border of the United States and Canada. Eastport is in the Bay of Fundy, a channel that opens into the Atlantic Ocean. So this entire purple highlighted area is the Bay of Fundy. Bay of Fundy is famous for its enormous tidal range. The top image shows a high tide. The bottom image shows a low tide. This map shows the tidal ranges in the Bay of Fundy. In some locations, the difference between high tide and low tide can be up to 16 meters. So if you were here, the difference between your high tide and low tide would be 6 meters. If you're here, the difference between high tide and low tide is 16 meters. Okay. Turbines, such as this one, are installed on the ocean floor. Currents from the rising and falling tides spin the turbines. This generates energy that can be transformed into electricity. The goal is to produce electricity for 2,000 homes. Before you begin the quest, consider your own experiences with tides. Discuss any patterns you have observed, or summarize what you have learned about tides during this kickoff. So, like, if you've traveled, all right, and you spent time on the ocean, not just, maybe for a day, or maybe for a couple of days, or maybe some weeks, maybe you did experience high tides and low tides, or maybe you've watched movies where people have referenced high tides and low tides, and they're like, oh, hey, the high tide's coming in a couple of hours, or whatever. So I feel like if you haven't personally experienced high tides or low tides, at least through this little quest right here, you've learned that, high tide, the water level changes at the shoreline. Low tide, the water, leaves and the water level goes down. All right, so that's kind of the kickoff. Okay, so as we go through this topic of Earth, Sun, and Moon, we will investigate tides and how they happen. But let's go back a little bit to Earth and space here. So with your table partner, what are some objects, or maybe just with yourself, you can just think in your head, what are some objects you might see in the nighttime sky? There's lots of objects you can see in the nighttime sky. You can see stars, the moon, satellites, meteorites, meteoroids, meteors, I guess, planets, comets. Maybe you see a plane flying through the nighttime sky. So lots of objects. So lesson 1 is movement in space, and I'm just going to focus on the night sky here, and specifically nighttime objects. So there's about 5 nighttime objects that are out in space that you can see. And the first one is the moon. The moon is the brightest and largest object in the nighttime sky. Okay. The moon is a natural satellite. Okay. So a body that orbits a planet, anything that orbits a planet, we call a satellite. But there are artificial satellites, like satellites for radio and internet and, communications. So we call those artificial satellites, like ones that we as humans put up. And then there's natural satellites, things that in nature, they just orbit that body, that planet. So like the Jupiter has many moons, all right? And we call them moons, but really we should call them satellites. It's got a lot of satellites. Planet, an object that orbits the sun. It has to meet like a couple criteria here. I think 3, at least in my astronomy book that I'm teaching to the astronomy kids, but it's got to be large enough to be round, and that is caused by its own gravity. And it has to clear the area of its orbit of any debris. So when we talk about how planets form, a lot of times it's like material being compacted because of gravity, and they all just kind of come together and collide. And we'll talk about how Earth formed, but things just come together and they collide and they become rounded over time. Okay, so it has to orbit the sun or a star or another body in space. So in this case, our solar system, it's the sun. It's got to be large enough to become rounded by its gravity and then clear any debris in its field. Now, Earth, as it's going around the sun, as it's revolving around the sun, it does come into some like leftover debris of its formation. And that's why, in August, we see the beginning of August, meteors. Okay. I can't think of the name. Oh my gosh, I can't think of the name. But as Earth is traveling around the sun, there are some like debris, and that debris burns up in the atmosphere, and you see those meteors or shooting stars, right? So here are some selected moons of the solar system with Earth to scale. So like Jupiter has many, many moons, but it has like four big ones, Io, Europa, Ganymede, and Callisto, and we'll go through them. Earth has one, it's the moon. Mars has two, Phobos and Deimos, and you can go on and so forth with the solar system here. Stars. Okay, a giant ball of superheated gas or plasma composed of hydrogen and helium. Stars, they make up constellations in our nighttime sky, which is a pattern of stars. And we, imagine them as a certain figure or an animal or an object, usually based on some type of story. In our nighttime sky, there are 88 constellations. So 88 groups of stars that form a pattern of some sort. So just in the northern hemisphere, these are the constellations that we can see year-round, and we call them circumpolar constellations. If you take a look right here, Ursa Minor, there's Polaris. Okay, that is the North Star, and you can see that it's kind of lined up right above Earth for north. And remember, Earth's tilt it's tilted 23.5 degrees. But these are the stars that you can see on any given night. Okay, at night. And you can see this is the Little Dipper, Ursa Minor. So its real name is Ursa Minor, but the nickname is the Little Dipper. Here is the Big Dipper, Ursa Major. Okay, so there's the Little Dipper there. So to find the North Star at night, what you want to do is you want to find a Big Dipper. And you look at the end of the Dipper here, and then you go straight up. And the star that lines straight up with it, that is Polaris, the North Star. Cepheus, every time I look at Cepheus, I think of a house. And here's Cassiopeia, and this is my favorite. It's the W in the sky. Okay, but these are the other constellations that you can see on any given night. Now, here's a map of the 88 constellations, and to reference where we are with the northern hemisphere, here's the Little Dipper. Okay, here's Cepheus. Here's the Big Dipper right here. I'm trying to find Cassiopeia. Oh, there she is. Cassiopeia. And then Orion down here. Now, Orion is a constellation, a seasonal constellation, and we only see Orion usually in the winter, like as we're transitioning into winter, and then you see it all the time in the winter, and then you see it the first part of spring, and then it disappears because it dips below the horizon. So we don't see all 88 constellations. We see a fraction of them. But the ones that we see year-round are over here. And you have to imagine Earth tilted at 23.5. And then as we travel around the sun, then more and more of these constellations are visible. Now, there are some constellations you'll never see from where we live, okay? Like the Southern Cross. So like people that live in the Southern Hemisphere, they never see the Big Dipper or the Little Dipper. Okay, they never see Polaris. They have different stars that help them guide them. So they have a star that actually lines up with the South Pole, okay, the South, and it is the Southern Cross. So that's, if you're navigating using stars, they use the Southern Cross. We tend to use the Polaris star. Okay, the last two objects that you can see at the nighttime sky: meteor, a streak of light produced when a small piece of rock or ice burns up as it enters Earth's atmosphere. So those are your shooting stars. And then comet, a cold mixture of dust and ice that develops and forms this very long tail as it approaches the sun. And when it's really, really far away from the sun, it doesn't really have a tail. Okay, it's like this dirty frozen snowball that's on its way towards the sun, and it will go around the sun and head off back to like the Kuiper Belt or wherever the heck it came from. If it's close to the sun, then it will start to heat up, and this tail with the gases start to warm up and then emit energy. Okay, so that's why you see the tail of comets close to the sun. So yeah. So just some differences between meteors and meteorites. So meteors, a streak of light we see. Asteroids were not mentioned, but I'm sure you have heard in the news how like, oh, there's an asteroid that's going by the Earth right now, and it's the size of 88 bulldogs. I saw that headline. I'm like, why would you choose bulldogs? They just choose the weirdest relative of size. Like, I can't even imagine 88 bulldogs. That's just not good for me. Comet, meteoroid, and your meteorite. Okay, so your assignment is to adopt a constellation. So in Google Classroom, there's a website in right here, and you'd click on it, and it will take you to it might take you to this page. And if it does, you just click on the first one, Northern Constellations. And there's some read-in if you choose to peruse through it. But what I really want you to do is scroll down, and it says here that the northern celestial hemisphere is divided into 4 quadrants. Northern quadrant 1, 2, 3, and 4. And there are 36 northern constellations found within these quadrants. Okay, and it lists all the quadrants that you would see year-round in the northern hemisphere. It has their real names. So the Ursa Major is your Big Dipper. Ursa Minor is your Little Dipper. There's my Cassiopeia. There's Orion. I'm trying to think of any other famous or well-known constellations. Maybe you don't know anything about the sky. Cepheus, which looks like a house. Cygnus, the swan. But anyways, I'm going to click on Cassiopeia. Okay. So in this assignment, you're going to adopt a constellation. And the worksheet. Oh, got to get out of full screen here. Worksheet looks like this. Okay, so you write your name, you pick out your constellation. If it has a nickname, put the nickname. So if you're doing the Little Dipper, okay, that would be the nickname, but you would put down for the constellation name Ursa Minor. And then there's this little area here for the history. Just give me a 2 to 3 sentence history of this constellation. How did this constellation come to be? What's the story behind the constellation? Because constellations, we imagined them. And they usually tell a story of some kind. Okay, so I love Cassiopeia because mostly of shape and the story. And if you scroll down, I'll just go back to the top. Nice little introduction here. Facts and location, where you can find it on the map. They'll show you a picture of what it looks like in the nighttime sky. Some of them are really good, some of them are not. But this is Cassiopeia right here. Perseid meteor showers. Those are the ones in August. If that doesn't help you with the drawing of the dots, you could Google image it as well, or make sense of this map, which lists the stars that make up Cassiopeia. But here, for that history, you're really looking for the myth behind it. And so the story of Cassiopeia was that she was a queen, and she basically thought that she was more beautiful than a god, and the god got really, really upset and decided to punish her by hanging her upside down in the sky, kind of like as her throne. And there's more to the story to it, but that's kind of the gist of it. She just thought that she could go against the gods, and she got punished for it. So now she hangs upside down in the sky for part of the day or something. So there's the history. And then you would draw out your constellation here. Now this table here, it says stars in my constellation. Some of your constellations are going to have a whole bunch. Okay, so I just want you to put 3. For the type of star, do not do that. Okay, we have not learned about different types of stars yet. Distance from the Earth, I do want you to put that. Magnitude, you don't need to put that. Color and surface temperature, you don't need to put that. Now, this website does give you magnitude, but the thing is you're going to be writing down numbers you don't understand yet. So I really just want the name and the distance from the Earth. Now, major stars in the Cassiopeia, they list them, and they will for all the other constellations. So you just pick some. But the thing I want you to realize is as you write down the name, and then you write down the distance, it says 228 light years distance. What this distance means is that light takes a long time to travel. I mean, light is fast, 300,000 kilometers per second, but Space is big. And so that star in that constellation, the light for that star to reach Earth takes 228 years. So when I look up at the nighttime sky and I'm admiring Cassiopeia, and if I were to pick out that star, the light I'm seeing from that star is 228 years old. So like if that star exploded right now, today, I wouldn't see that explosion until 228 years from now, and I wouldn't be around to see it. Okay? So you write down 3 stars and the distance from the Earth, and then 3 fascinating facts that you learned about that. If you go on through, I want to say, okay, there's a lot of stars here. I'm just going to not do that. For the interesting facts, you might have to scroll back up to the top. Let's see. I might pick out that it's the 25th largest constellation in the sky. It's found in this quadrant. This is the area of the constellation. Whatever. Where it was first cataloged by Greek astronomer Ptolemy. Whatever. So that's the assignment for Adopt a Constellation. And if that's confusing, the backside does another great description, but just keep in mind that I don't want you to do type of star, magnitude, and colors / surface temperature of area. And they give a different website. So that is today's lecture in a nutshell.